Anytime anybody says something about radiation, most people hear the term radiation and are worried about it. And so let's talk a little bit more about radiation and its impact on living organisms. So when we measure radiation, it's usually measured using a Geiger counter, or more formally, a Geiger-Müller counter, named after the two scientists who worked on this. And the way that a Geiger counter works is that it measures ionizing radiation events. And by ionizing radiation, we're talking about any kind of ionizing radiation events. So it could be alpha, it could be beta, it could be gamma particles, any of these that are associated with radioactive decay. But they aren't just from radioactive decay. You can get cosmic rays and stuff that come in here too and can be detected. And so you have a normal amount of background radiation. And this background radiation is due to cosmic rays. It's due to radioactive particles in the soil. I'll just say in our environment. And there's a certain amount of this that we are exposed to all the time. And largely our bodies are used to correcting any potential problems that come up when we experience background radiation, and so it's not a big deal. So inside a Geiger counter, let's actually go ahead and take a look at a diagram here. All right, we're over here at Wikipedia again. And one of the reasons I like using Wikipedia is that all of the images that are included in Wikipedia are Creative Commons images, and so we can use them without needing to be concerned about copyright issues. So inside a Geiger counter, you have an inert gas that's represented here, and then the ionizing radiation can come in. In this particular diagram, it's allowed to come in through this window that's on the right-hand side. So the ionizing radiation is this swirly little yellow arrow here. It hits one of our gas particles and ionizes it. And so when it ionizes the gas particle, that is doing exactly the same thing that we've talked about in the past for ionizing. It kicks an electron off of the particle. So from this other diagram, you can see that this little rod that goes through the middle of the chamber is going to be charged with a positive charge, and then the outer part of the chamber is going to be given a negative charge. So when we kick off an electron here, the electron will go and head toward the anode part, this positively charged part labeled here, and the negatively charged the positively charged gas particle that results is going to head toward the negatively charged outer area of this. So when this happens, then the electron creates a change in the electrical charge, and that's what gets counted here on the counter. And then as soon as the gas particle hits the outer part of the container, it gets an electron back and the chamber is reset. So that's functionally how a Geiger counter works. Now the thing about Geiger counters is that they count all kinds of radiation equally, so they can't track individual kinds of radiation. They also, if you get too many radiation events, then the instrument can't reset itself fast enough, and it will actually undercount how many counts you get. So let's talk about how we count them. So when we count radioactivity, the original way that we counted these was in terms of decays in time, so like decays per second. Would be one way of looking at this. This would be a radioactive decay event. And the original unit that we used to talk about this was the Curie, named after Marie Curie, of course, and it's given the abbreviation capital C lowercase I. Now, this is actually a really huge unit. And so now we use the becquerel as well, also named after Henri Becquerel, who was also important in discovering radioactivity. They both got the Nobel Prize for it, if you remember. So 1 curie is equal to 3.70 times 10 to the 10 becquerels. And 1 becquerel is equal to 1 decay per second. So you can see that 1 curie would be a gigantic number of decays per second. And so as a result, curies don't tend to get used very much because the amount of radiation that you would be exposed to, if you got exposed to a curie, would probably just kill you right off. So these 2 units here, these are tracking decay rates. But these also don't distinguish alpha, beta, and gamma radiation. It's any kind of decay, any kind of radioactive decay. So rather than just tracking decay rates, our bigger concern is what is this doing to living organisms? What is the impact on living organisms? Of whatever the amount of radiation there is. So all of these have to do with ionizing radiation that we've mentioned a couple of times. And the reason why ionizing radiation is dangerous is because it can ionize your body. I mean, not your whole body. Usually, DNA is what we're concerned about inside any kind of a living organism. And what happens if we ionize DNA? This damages the DNA. And if you remember, DNA is the instructions in your body for how to do all the things that your body needs to know how to do. So if you damage the DNA, you're damaging your set of instructions. Now, bodies can repair and do this all the time. They repair DNA constantly. Your body has all kinds of safety mechanisms inside your body. Part of the reason why the DNA is a double helix is because if part of it gets broken, then the body can look at what was on the other side of the DNA and replace the parts that are missing by matching them up appropriately. And they've got, proprietary pairs in the DNA. And bodies are repairing DNA all the time. The problem is, of course, that the more damage that you have, the more chance of making a mistake your body has. And the mistakes that are problematic are not the giant ones, right? If your body sees DNA and he says, oh, lordy, this DNA is so damaged we just can't do anything with it, then your body has a mechanism for just scrapping that cell, sending it to the recycle heap, and using those resources again. What's the problem is that if you have some minor problem with the DNA and then the body either doesn't notice it or fixes it wrong, then this can cause cancer. And so ionizing radiation is related with increased cancer rates of all different kinds of cancer, just depending on what kind of ionizing radiation we're talking about. And although we're talking about radioactive radiation specifically, ionizing radiation includes alpha, beta, and gamma radiation, but also X-rays and some UV. All of these can be ionizing radiation. They can break bonds. They can break chemical bonds in molecules inside your body or on your skin or whatever. And that's what's causing the damage. All right, so the thing is that different kinds of ionizing radiation can be problematic to different parts of you. And depending on what kind of radiation you're experiencing and where that radiation is, the amount of ionizing radiation dose that you get can vary. So the dose of radiation received is tracked two ways. In SI units, you have the gray. I've never actually seen this unit used. But 1 gray is equal to 1 joule of energy per kilogram of tissue. So, if we were looking at you and your body and you had just gotten a dental x-ray, then we would look at the joules, how many, what the energy was of that particular dental x-ray, and then we would look at how big your body was, how big the tissue is in your face area that got exposed to the dental x-ray, and that's how we would figure out the amount of exposure, the radiation dose that you had received in gray units. But as I said, we don't actually see gray units very often. More often, I see people using the sievert. And the sievert is adjusted. This is also an SI unit. So, not ST, SI. This is adjusted not only for the amount of tissue, but it's adjusted by the penetrating power of the radiation too. So the way that that's going to look is it's called the relative biological effectiveness. Or RBE. So 1 sievert is equal to 1 gray times the RBE for whatever the amount of radiation is. So let's go and look at a couple of tables where we can see some of these values. All right, this is table 19.3 from our book. These are the different RBE values for different types of radiation. So you can see that gamma rays have an RBE of 1 and beta particles are a little bit higher. Neutrons are heavier than the gamma radiation, and because of course gamma radiation is just light, it doesn't have mass. And it's quite a bit heavier than the beta particles, those are electrons. So those are a little higher. Protons would be higher still, and alpha particles are even higher. But at the same time, the radiation penetrating power of each of these different emitted particles varies as well. So this is a second complication in our figuring out how much effect these different radioactive products might have. We talked about this a little bit before. This is figure 19.10 in the book. And this is our alpha particle, and you can see that it's stopped by as little as a piece of paper or the dead skin cells on your body. So if those alpha particles are staying outside of you, then the alpha particles, even though they have a higher RBE value, aren't going to be causing tissue damage because they aren't going to be penetrating into your skin. The beta particles, on the other hand, and the gamma particles both have sufficient penetrating ability to pass into our body in the case of the beta particles and pass all the way through our body in the case of the gamma particles. So both the beta and the gamma radiation are extremely penetrating and can be problematic even if we are just around them. So this is both good and bad. The radiation can be used therapeutically as well. So when we are looking at these different kinds of radioactive products, then different cancer therapies actually use radiation to try to kill certain tumors. And very highly focused beams of these radioactive products, probably mostly gamma radiation, is used to kill cancerous tissues. Now, of course, they also kill some of the healthy tissues that are there, but generally speaking, it tends to be a good therapy regardless. I don't know, it's certainly very traumatic to the body still, but it is used in a lot of different cancer therapies. Let's take a look at some of the radiation dose health effects just in general, and then we'll look at some very common exposures to our radiation sources. This is table 19.5 in our book, and so at very, very low doses, this is below 0.25 sieverts of any particular kind of radiation, then there are no immediate effects, but potential long-term carcinogenic effects. Once you get past that 0.25 sievert dosage, though, you're starting to see some pretty significant effects. This is just going to be an effect on your immune system, but then after that, you're going to start seeing some really significant effects. So these guys start to get a little scary here, right? And when people have had exposures at sites of the meltdowns, like in Chernobyl, you're getting some really significant radiation exposures. However, most of the time we don't get anything near this. Let's actually go back and look at the image of common doses of radiation from different activities that people just do on a regular basis, so we can see where that's out. But what I want you to remember here is this 0.2 sievert effective dose. This is an image from the EPA.gov website, and what I want you to notice here is that these units are in millisieverts. So let's take a moment and remember what the numbers were that we were just looking at. The high end of our range for sievert was 0.25 sievert. 0.25 sieverts. This was the max with no obvious health effects. Okay. So this is a quarter of a sievert. So if we're talking about a millisievert, that would be sieverts divided by 1,000, right? So this would be 1 millisievert. 1 millisievert would be 1 sievert divided by 1,000. Okay. So when we're talking about millisieverts, this is the decimal place that we're talking about, okay? So let's go back and then we'll translate those millisieverts into sieverts and we can look at them. All right, so 10 millisieverts is if you get a whole body X-ray functionally. If you have a smaller X-ray, then you might have something around 6 millisieverts. If you have some other X-rays, they all kind of go down from there. Over here we've got a head CT, over here we've got a mammogram. And then you get a certain amount of radiation just for living on Earth. So let's go back to our table here and notice that our maximum on that normal events table was 7. Excuse me, was it 10? Now I can't remember. Let's go back over. Oh, 10. All right, 10 millisieverts. All right, so that's 10 millisieverts. All right. And this is if you get a whole body X-ray. Everything else is less than that. And you can see that this is more than 10 times smaller than that maximum dosage with no noticeable effects. Let's look at a different image that has some other common activities. Here's another fact sheet from the University of Michigan website. And this one is looking at different sources of radiation relative to each other that you would naturally experience just, in general. So the biggest source of our radioactivity in our lives is from naturally occurring radon. That's this 228. We've switched units here. We're now on millirems. So we'll go back and review what millirems are here in just a second. So then our next one down is cosmic radioactivity. That's this one. This is if you live up high like in Denver. The next one is your standard chest x-ray mammogram. And then the next smaller one is just natural radioactivity in the body, because we have a certain amount of radioactive isotopes that have absorbed into our body from all kinds of sources, from foods that we've eaten, from air that we've breathed, from different little dust particles that we've absorbed. And so this is just from living on the Earth. Here's a chest x-ray. And this is from living near a nuclear power plant. So you can see it's a much smaller one compared to these other naturally occurring sources. So, at any rate, we need to talk briefly again about what millirems are compared to millisieverts. So let's go back to that other image because it had both of them on the same image. This is our EPA website. Again, you can see that 1,000 millirems is the same as 10 millisieverts. So that means that there is 100 millirems in 1 millisievert. So let's go back over there with that unit conversion factor in our heads. All right, 100 millirems is equal to a millisievert. So 228 millirems is, 2.28 millisieverts. So going back to our scale page again, if we have 228 millirems, that equals 2.28 millisieverts. And so that means that that would be 0.0028 sieverts. So this is from radon, and that was on our diagram as well, that these naturally occurring sources of radiation are much smaller than most of the other things that you will experience. So unless you happen to be near some nuclear disaster event, you're unlikely to get a significant amount of radiation from any source. Even standard routine x-rays, these are not exposing you to more than what you can safely absorb in a year. So under most circumstances, all of the medical imaging that you get is still probably going to be less than your natural exposure to radon. So let's just review for a minute here. We've talked about various different units, that we had the Curie and the Becquerel. These are both just looking at the rates of decay. And then when we talk about exposures, we're most commonly using sieverts, or really millisieverts or millirems, to look at how much radiation bodies are getting exposed to.